I learned a lot this week. I hope you can learn a little bit in this talk. So let me first go a little bit through the general things, then through the current measurement, and at the end about a little bit improvement. So I think you all know what the magnetic moment is. It's the coupling constant between the spin and the magnetic moment. So we are interested in this property here. And so the nice thing about muon is it's a bare lepton, and you basically can write it down in Feynman diagrams. The Dirac term is 2. We have all these other contributions from higher order corrections, and that's the part which we call this anomalous magnetic moment, everything which deviates from 2. And yeah, you can have contribution from beyond standard model physics, and as Pierre just said in 2 talks before, if you do a naive scaling, you have here this lepton mass squared. That's why even if the measurement is not that precise as for the electron, the contribution to new physics is maybe larger. To split up the muon G-2 in the standard model, we have parts from QED. You can calculate it perturbatively up to high orders in loop. Same for electroweak, maybe not so high orders in loops. But the hadronic parts, it's you cannot calculate perturbatively, and they are derived either data-driven or from the lattice. And these are the parts, the contribution and the uncertainty given to the final number, and I find it nicer to represent it that way. So your contribution is basically only QED, but your error comes mainly from that hadronic part. There's a theory initiative of more than 100 theorists which sat together and tried to collect all information to really come to a consensus on that number before the next experiment was done. And that's the value they published in their white paper, basically a year before the measurement came out. And so this is the status of A mu over the years. So it was already measured in the 60s. That's basically the latest measurement from BNL. You see the data point also here. And you see that over the time also the theory evolved, and that's finally the white paper model. And at that time, there was a 3.7 signal discrepancy. And so, of course, you want then to measure it better. And we wanted to reduce the uncertainty of BNL by a factor of 4. So how do you measure that? You put a muon in a homogeneous magnetic field, and then you have 2 effects. The first one is you have cyclotron motion, which is given basically by your B field, and you have spin precession. And the nice thing, if you compare these two, or you just measure the difference, which we call the anomalous spin precession frequency, you find out that this is actually proportional to G-2 given and the magnetic field. So what you do is you polarize your muons, you put them in a storage ring, let them precess, and measure how this angle evolves, this anomalous spin precession angle over time. Of course, it's not that easy. You don't have a super homogeneous field. You have relativistic effects, electric fields. So this is the part we just looked at. This part comes from the fact that the electron also have transversal component and are not perfectly perpendicular to their motion. This part comes from additional electric field. The nice thing about the second term is that we already have a quite good knowledge about mu itself, and this is a difference. So you can choose the gamma factor, which corresponds to a momentum, such that this bracket basically cancels and you get rid of all the effects. So later we will see these will lead to corrections. So let's go with this one. I just rearranged it that we have now a mu here. And to make it easier, you now express your magnetic field by NMR techniques. And that's expressed by the proton spin precession frequency. And the nice thing then is that you can express this as a ratio of good known quantities. That's the ratio of the magnetic moment of a proton to an electron in hydrogen. That's the bound state QED calculation. That's known exact. And that's the mass ratio, which we know from the muon hyperfine splitting. And that's the electron G factor. And so if you add that up, the uncertainty in total are about 24 ppb. And our job now is to measure this ratio, the anomalous spin precession frequency compared to the proton spin precession frequency, which is express the beam field. When we do that, you basically have, again, here this omega ray and this omega p. In addition, you have correction terms to whatever we neglected before. We have to calibrate things. We are only interested in the magnetic field where the muons live. And we also have transient magnetic fields. And we will go through it now in smaller steps. So the experiment is located at Fermilab. You start with a proton beam and you send that on a beryllium nickel target producing pions. And the nice thing about pions is that they decay with a weak force, and that's polarity violating. So you directly end up with a polarized muon beam. Then you have a momentum selective beam line, and that we tuned that it's this magic momentum which cancels out this later correction factor. And to get a pure lepton beam, you let go the beam several rounds through this delivery ring, and then other particles with different mass are outrun. So you basically wait till they separate in time, and then you're left with a pure muon beam. And so we get about 10,000 muons every 10 milliseconds, and they are then bunched. When they are bunched, they enter our experimental hall from up here, and we have the superconducting magnet, which you see here, the steel and blue. That's a return yoke. We have here in yellow marked, these are our superconducting magnet coils. In total, the magnetic field is vertically 1.45 Tesla. And then in the middle, you have the storage region for the muon. It's not that easy to get the beam directly into the ring because if you put it into a magnetic field, it goes on the circle. So you have here to locally cancel the magnetic field. That's what we call the inflector magnet. It's a superconducting setup where you see here a simulation of the magnetic field, so that you have here a small region where the field cancels and you can inject the beam into the ring. So if you have that, and it now starts to see the field, it goes onto an orbit, but after one orbit, basically, it would hit the inflector again and your beam would be lost. And the ideal storage orbit is slightly shifted, 77 millimeters, so you have to do something. The ideal thing is to do to it here, and we call that a kicker. That's in the first pass, you have to lower the magnetic field by 2%. And because the revolution time is 150 nanoseconds, that has to happen really, really fast. So these are our kicker plates where we apply a high voltage pulse just for the first 150 nanoseconds to get the muons on the storage orbit. And yeah, then basically this field should vanish again. Besides that, once the muons are in the ring, we want to keep them in the ring, and we need to focus them. Therefore, we have here these electrodes, which form a quadrupole field. So we apply high voltage to it. That focus your beam in the vertical, but defocus in the horizontal direction. but the magnetic field counteracts the defocusing in the horizontal direction. However, due to that, you get a lot of beam dynamics effects. This is basically a quasi-panning trap, which covers 43% of the ring. So to not pile up plasma in there, we have to run this in a pulsed mode, where pulsed means it's static on the time scale when the muons are present, but in between, we release the charge. So now, how do we detect that? Now, again, where is the weak force? When the muon decays, there's a preferred direction for the positron to come out. And depending on your energy, you see here the asymmetry in the emission. That's basically the same thing as a function of energy. You see here the asymmetry curve if you look at the line labeled by A. And then you have to boost that into your laboratory frame. And again, you see you end up with an asymmetry depending on your energy. So if that's a 1/12 of the ring, that's our vacuum chamber. Here, this is a normal muon storage orbit. Now, it decays and the positron is lighter, so it spirals in. We have here the stations, that's a calorimeter where we can measure the time and the energy. And in addition, for 2 of these calorimeters, we have these trackers which give us information about the beam profile. These are the trackers, it's raw trackers filled with gas, and you can nicely see how we can reconstruct the beam, and you see it oscillating because of all these beam dynamics effects, and that's basically the input to additional beam dynamic simulations. Then we can basically calculate how the beam is at every point around the ring. They are located here and here, and then the positrons are detected via these calorimeter blocks consisting out of 9 × 6 crystals. In there, you produce Cherenkov light, which gives you a very fast signal because the timing is important. And they are read out by silicon photomultipliers. And what you then observe is, as a function of positron energy, your count rate changes. So if you apply a simple threshold here, with time, you see that depending how many electrons are gone, you get this, we call this a wiggle plot. Right. This, of course, depends on the energy threshold you put. So depending on the energy, the asymmetry is different. And you can either weight it by the asymmetry or simply apply a cut threshold. And then we observe these muons for about 10 lifetime, the mean lifetimes. And our job is basically now to measure the frequency of this wiggle. It's basically this exponential decay, and then the cosine with this omega A, which is this anomalous spin precession frequency. However, whatever changes the phase over the full time of the muon storage will bias the frequency. Whenever you have something shifting the phase at early times to late times, you get a bias to your frequency. That's very important. We have only one laser that's set up here. It's injected all the time, about 10% of the time, also while data collection, into our crystals, and just is there to monitor the gain of our light collection. That can then, in the long term, correct things like the gain change due to temperature, or in the short times, like the initial flash. When you inject the beam, there's a flash where your gain drops, and also if you have pile up, basically, you can measure the crystals. Okay, this is a wiggle plot, or the starting point of this. We had this formula before. You can average all these thresholds if you, or the asymmetry and the phase. if you apply a threshold. And if you do basically this fit, that's your residuals. And you would say, okay, that doesn't look so nice. You can do a fast Fourier transform of that, and you see, okay, there are clearly things in there. And actually, you have to account for all these beam breathing, vertical oscillation of the beam. And if you do that, you can nicely model that. You have to put in these beam dynamics, and you get a 22 parameter fit. But afterwards, your residuals are super flat, and your chi-square is also very nice. Okay, this explains this quantity. I quickly just want to flash what these corrections are. The first one is coming from the electric field. So we assumed we inject particles at this magic momentum. However, you have a finite momentum spread, and thus it does not cancel exactly. However, we can calculate the momentum spread because we have a bunch beam sent in, but with time this debunches just by the momentum spread, and we can calculate that and calculate a correction factor from that. The second thing is that you have a pitch that's basically the vertical component of your beam. That's proportional to the amplitude, and we can measure with our tracker system how large this amplitude is, so you can also correct for that. You can also lose muons, not to decay, but by hitting the walls or collimators or things like that. That would be such an early to late effect, and you can measure basically the loss rate for high energy and low energy muons and compare that. Based on that, you can get also a correction factor. And the last one, it depends on where exactly. So if you have a high energy event decaying at the outers at a higher radius than a lower one, your timing and asymmetry can be different depending on how it gets into your detector, and that has to be also corrected for because it's a phase acceptance correction. Okay, the next thing is the magnetic field, and we have several devices for that. We measure the field, as I said in the beginning, using NMR probes. And this device, we call this a trolley. It has rails, so we can pull it through the ring. And this allows us to measure the spatial field distribution in the ring. We do that about every 3 to 4 days. Here you see the individual probes. And because at that time we cannot have muons, that's bad. We have to still monitor the whole field all over the time. Therefore, we have a system called fixed probe system. These are probes which are located all around the ring in the walls of the vacuum chamber. So this is a storage region. This would be the size of the probes inside the trolley. And here you have these additional probes in the region of the vacuum chambers. And with that, you can track it, the magnetic field 24/7. What you then have basically, using the trolley, you can make these field maps also as a function of azimuth. We then express that in terms of the multipole expansion, so dipole term, normal quadrupole term, and higher order terms. And then we use our fixed probe data to interpolate between two trolley runs, which are typically 60, 70 hours apart, and we nicely can track the field in between. That's about this part here. We express our field then in the spin proton precession frequency, but we also have to convolute it with the muon distribution. Here you see in this plot overlaid. So in the background, that's an average magnetic field around the ring. That's these contours. And in color encoded, that's the averaged around the ring muon profile. For the run 1 data, you see it's slightly off center. And then you basically convolute this to get the field that the muons have seen. You also have to calibrate the field. So the trolley probes are the thing which really measure the field. So the fixed probes only track differences. So this needs calibration, and we have an absolute calibrated water NMR probe. This is cross-calibrated at the Argonne National Lab, also with the helium-3 standard. And what we then do twice a year is we have this on a 3D translational stage, and we can move that into the ring. And then we move the trolley to this position, align the probe with the probes in the trolley, and then we swap back and forth to basically translate this calibrated probe or absolute calibrated probe to the trolley probes. We also have transient magnetic fields. There's this term here, for example, from the kicker. That's the thing I explained at the beginning, where you have to reduce your field or increase your field in the first turn. That's super fast, and your NMR probes don't see that. Your fixed probes are also see a reduced effect due to your shielding. So you need something fast. We use a crystal or make an optical Faraday rotation measurement, where you have here lasers sending in, going through the g-2 crystal, where you have Faraday rotation, and then you can, by measuring the return light from the two polarization stages, you can conclude back on what's your magnetic field actually as a function of time, just while that kick. You see here this device while a calibration measurement in between the kicker plates. The second transient effect are from the quadrupole transient, and as I said at the beginning, we pulse them. And this pulsing somehow leads to a magnetic field that changes over time. We assume it's due to mechanical vibrations of these plates induced by eddy currents. And what we did is we inserted a probe in here while pulsing these plates, and then measured with a fixed time delay this pattern really precisely. And actually, if I zoom in here, this gray region, that's the time when a muon is present. And as I said before, it's bunched, so you have several of them. And you see this field doesn't correspond to 0, so we have to correct for that the field in this time is slightly off, but on the PPD scale. Okay, with that, we also have this. Basically, we have now all coefficients. So we can look at the ratio, and in our run 1 data taking, we had basically 4 major data set, because all that depends on your kicker settings and your quadrupole settings. These influence your beam dynamics, and so you get different running conditions. They are okay to all give the same result, but at that time, our result was still hardware blinded. So this hardware blinding worked as follows. We had 2 colleagues from Fermilab who the reference clock for this omega ray measurement was supposed to be a 40 megahertz clock, but they actually detuned it. This was hidden behind that cover. And then we had a large collaboration unblinding where we all met online, and let me thank at that point the full collaboration for this tremendous effort. And just after everything was signed off, they online opened, so they sealed this number in 2 envelopes. They plugged out these numbers, and this 40 megahertz clock was basically this number here. So online still, while that event, they put it into their plotting script, and out of that came this plot. We see this result nicely agrees with the previous measurement from BNL, and the error bars are about the same size what we know before. Then you see these indicate the statistical and systematic error, so they are both statistically limited, so you can average them nicely. And at that point, there was this value from the theory initiative, and you get a difference of 4.2 sigma. However, basically the next day, a new result came out. This here from the lattice calculation. And so, as I said in the beginning, all our uncertainty in the theory comes from these hadronic parts, especially from this contribution here. And you have these two ways to either calculate with this dispersive approach, which is basically always done, or all results going into this white paper were relying on this dispersive approach. And this publication was then the first publication which had competitive error bars and recalculated this contribution. And with this, you end up here. So this is a new error of comparison, this anomalous magnetic moment, where you have here the measurement, here the lattice calculation, and here this dispersive approach. And you have discrepancies. I wouldn't say these are really significant. This is a little bit more significant. Right. So if you want to interpret that, this disagreement is large. For example, if you would make the difference between those two, this is about 1.7 times the correction you get from the electroweak diagrams, from all electroweak diagrams, right? So we wouldn't, if you don't know that electroweak force exists, we wouldn't have seen it, right? It would only be 1 times this factor. And if you go with this naive new physics scaling approach, you can estimate that your beyond standard model physics has to lie on a scale of less than 2.1 TeV, which is hardly compatible with LHC and dark matter results. So that's again the formula I show all the time. This is now our error budget for run 1, where you have here the corrections, here the uncertainties. And these are our design goals. You see that this table is fully dominated by our statistical uncertainty. So we have to take more data. But if you sum up all these contributions from the systematic uncertainty, you still see we don't yet make our design goals. So we have to improve either by improving on the running condition or by identifying more systematic effects and better understanding them and quantifying them by making special calibration runs. And I have brought one of these improvements here. So this is the magnetic field stability while this run 1. You see here the 4 data set. And you see here, so this is expressed as these multiple moments I mentioned before. And you see here these wildly oscillating. And this is a diurnal variation, which is caused by the Hall temperature. What happens basically is that your magnet yoke warms up and cools down, slightly extends, changing the gap between your poles, and this then you directly see in your magnetic field. So after this run 1, we went and put all the magnet into blankets to better isolate it. You see we significantly reduce the spread in temperature, but this was still not optimal. So after run 2, we did a major upgrade to the Hall cooling system. And here you see basically the temperature change while run 1. And in run 3, it's pretty flat. And you see also that on that scale, the magnetic field is super flat. Right. With that, I come to the summary. As I said, we have to collect more data. What I showed is the published run 1 results. Since then, we are collecting more and more data. The run 2 and run 3 data are currently in the analysis. They are still blinded, so I cannot tell you anything about it because I don't know myself. Run 4 is currently in the reconstruction processing basic data quality phase. And in run 5, we are currently still data taking. We try to improve our systematics further and further by either these improvements in operations or by special calibration measurements to understand and characterize our systematic uncertainties better. And yeah, by now the increase in statistics is a factor of 8. The outlook is this summer, we actually will have a major change in the experiment where we will change the experiment from mu plus running into mu minus running. With that, we can then test Lorentz violation, CPT invariance. That's a major work. And there are other experiments upcoming, like the JPAC G-2, which uses different technique. They want to get rid of this energy E-field dependent term completely without using any electric fields. But therefore, they need a very cool, basically no transversal momentum spread. And yeah, for the theory side, we hope that there comes an agreement on the QCD, latest QCD results, and there's also a proposal to renew the data for the data-driven approach. With that, thank you for your attention, and I'm happy to take questions.
Thanks very much for the very nice talk, René. So Dima has a question.
Ben or?
Thanks so much. I have a question. Do you use the old muon trick?
Old muon trick?
Yeah. So it's if you don't look at the first part of your,
yeah.
You know what I'm talking about? Yeah.
Yeah. So actually, so when we look at that wiggle plot, now let's go back quite a bit. Here at the beginning, you are you have all the complications because you just injected your beam, you have the splish and all that. It depends on the analysis. We have 11 different analyses trying to measure that. Depending on that, you start your fit at either at 30 to 50 microseconds, depending, and you just throw away the previous part.
Have you tried like looking at the like very old ones, and then the line will be very narrow, but at the expense of the statistics, right?
Yeah, then your statistics heavily goes down. So
the line is narrow.
But he looks at everyone.
Yeah. I'm pretty sure that they optimized this effect. So the start point variation. I think every analyst had to scan their starting point and see that they are not influenced by the exact choice of that.
And but you're gonna switch to negative muons, and I mean, positive muon mass is known well enough, hopefully, for your goals. But the negative muon mass is known very badly, and much worse than what that. So for a CPT test, you'll have, I think, to take the positive, to assume the negative muon mass and the positive muon mass are the same. That's not so bad, but it's not the same.
Yeah, I guess that will go then in the error budget of the comparison.
I don't think the error budget, because you will probably take the positive muon mass to be the same as the negative muon mass. But the negative muon mass is very badly known.
That might be right. Yeah.
Any other comments or questions? Maybe one very quick one from my side. You just said you have a factor of roughly 8 times more data now compared to what you've published, which gives you roughly a factor of 3 in the error bar. How about all these improvements in the stability of the experiment? So what do you eventually expect in units of fractional resolution?
So in total, we want to be a factor of 4 better than the BNL result. And currently, I think we are pretty confident that we will make that with finishing this current data taking period.